As a women's basketball player, I enter Lockridge Arena often. I noticed that when you open the door to Lockridge Arena from the lobby, you feel a strong gust of air flowing from the arena through the door and into the lobby. I immediately thought of fluid mechanics and modeling this airflow with concepts that we have learned. So I think you can imagine this airflow as a Venturi meter or an orifice meter, as the diameter that the air can flow through is greatly reduced from the arena to the doorway. When looking at the continuity equation and assuming that density is constant, we find that because A1 is much greater than A2, the velocity through the doorway, V2, must be much greater than V1. Due to this airflow through the doorway, I realized that the pressure inside the arena must be greater than the pressure in the doorway. So P1 must be greater than P2. Therefore, when the door is opened, air flows through the door from the arena into the lobby due to this pressure differential. So this can be seen by applying the Bernoulli equation, making many assumptions. So the velocity of air through the door is greater than the velocity of the air in the arena. So we can consider V1 to be negligible, about 0, when applying the Bernoulli equation. We assume that there is no change in potential energy from inside the arena to the door, because delta Z is approximately 0. So the velocity of air through the door depends only on the change of pressure from inside the arena to the doorway, and on the density of air, which we will assume to be constant for simplicity. By changing different parameters of this equation, we can get different velocities. So say we increase or decrease delta P, then the velocity through the doorway will change. We can revisit the continuity equation and see that the velocity through the doorway also depends on the velocity in the arena times the area of the arena divided by the area of the doorway. So changing these areas can also affect the velocity through the doorway.
Hi, and welcome to Megan's Spontaneous Lecture. So, a few weeks ago, I was driving in my car and I wanted to wash the windshields with the windshield wiper fluid. However, it was empty. So, when I got home, I took out the funnel from my car and the extra windshield wiper fluid, and I filled the empty fluid container. And while I was doing this, I noticed the Bernoulli equation phenomena that we'd been talking about in class in action. And that's where A1, which would be up here, is much greater than A2, which is down here. So we could consider V1 as much less than V2, and we could actually consider it negligible in calculation. So here's a short clip of a funnel in action. So while the area difference in this problem may not be big enough to cancel out V1 in the Bernoulli equation, the concept can definitely still be seen. When a fluid flows through the funnel into the container below, which would actually be the washer reservoir in a car, the rate of change of the height of the fluid in the bowl-shaped part, which represents V1, is much smaller than the velocity in V2, which is this tube part. You can see this as I poured water through the funnel. You have to wait for the fluid level to drop before you can pour more water, or you will overflow the funnel. We also know that P1, which is up here, would be atmospheric pressure, while P2, the pressure in the tube, would be due to the pressure of the washer fluid. If we look at a snapshot in time, we can consider it as the hydrostatic pressure from the fluid. When setting up this general equation after simplifying our assumptions, we can observe a few things. When setting up this general equation after simplifying our assumptions, which would be that V1 is approximately 0, P1 equals P atmospheric, and that Z2 is defined as 0 compared to Z1. What we can see is that the velocity and pressure terms are greater on the outlet side, while these terms are less on the inlet side. Thus, we can conclude from observation and the equation that the potential energy term GZ1 must be larger in the bowl than in the tube for the two sides to equate. In fact, GZ2 is 0. And this shows us that the potential energy is transformed into kinetic energy and increased pressure energy in the tube. So this is what a snapshot in time would be like. You have atmospheric pressure, which would actually cancel, and you would have all of the potential energy turning into hydrostatic pressure and velocity if you look at one moment in time. However, you cannot always say that P2 equals P atmospheric plus rho GH when the fluid is moving. Thus, we take a look at one moment in time. And another way that we can relate the velocities without canceling them out would be via the continuity equation, where m dot 1 equals m dot 2. You know that density is constant, so you can cancel those out, and you get v1a1 equals v2a2.
All right, I'm going to be doing my spontaneous lecture on a fish tank cleaning tube. So back at home at my parents' house, I have a fish tank, so I've used this or seen it used many times myself. So basically the purpose of this is every couple weeks you need to change the water in a fish tank, and because the water gets dirty, and also there's kind of crud and dirt that gathers at the bottom in the gravel. So it's used to clean out the water and clean out some of that dirt at the bottom. So how it works is first you fill up this whole tube. The tube has a fatter end at one end, and then it's a skinnier tube all the way down to a discharge bucket. So you fill up the whole tube with water. There's a couple ways you can do this. One is you can just cover up this end with your thumb or something like that, and just pour water into here or scoop water into this end. The other more old-fashioned way, this is how I always saw my dad do it, is you would just suck from this end until you get almost to the very end, and then that'll fill the whole tube with water, kind of a vacuum effect. So how it actually works, it's similar to a siphon, a gas siphon. As long as this discharge bucket is below the level of the water will just flow through the tube, and this is due to the Bernoulli's equation, because this is at a lower elevation. This discharge bucket is at a lower elevation than the level of the water. So I'm just going to show a quick YouTube video to give a little bit better visual, since I don't have an actual fish tank in front of me. So here's that.
Fill with water. Then all you do is turn upside down, put your spray hose back in here, and then let it go. As you can see the water here. When I go down inside the gravel, get all that garbage out.
So hopefully that gives a little bit better visual of how this actually works and what its purpose is. So now I'm going to explain the fluid mechanics behind it. So this is an application of the Bernoulli's equation because the water is flowing as the elevation changes. So there's a couple different ways you can apply the Bernoulli's equation depending on what variables you're looking for. So if you're looking for the velocity in the tube, you can define your 0.1 as the top of the water and your 0.3 as the discharge, the end of the tube into the discharge bucket. So at this point, both the pressures are atmospheric, so they cancel out, as you can see down here. The velocity at 0.1 is pretty much negligible, so that goes to 0. And our z value at 0.3 we're calling 0. So this just gives the velocity coming out of the discharge as a function of the height of the level of the water. The other thing you could be looking for is the pressure in the tube, which is shown up here, or at a given point, 0.2 up here. So then you do your Bernoulli's from 0.2 to 3. Your pressures don't cancel out in this case. However, your velocities do, since the diameter of the tube stays the same, so your velocities would cancel out. And as well as your Z3 value, since that still goes to 0. And then you could find the difference in your pressures as a relation to the height, Z2. So that's my spontaneous lecture. Thank you very much.